So I welcome you back in this lecture series on refrigeration and air conditioning experiments. In the previous session, we have seen the trial on vapor compression cycle test rig. In this session, we'll be discussing heat pump test rig. Hi, this is Parag Desle and you are watching Bodh Nidhee. Here I bring educational content for engineering students. So if you are new, please consider subscribing for more. So the content of today's trial on heat pump would be, firstly we will discuss what are the prerequisites that are necessary to understand heat pump and its analysis. Then we'll discuss the setup diagram for the today's experimentation. Then we'll go for specifications, assumptions that are necessary for the trial. And then we'll discuss what is the observation table that is required to record the readings on the setup. Then we'll go for the setup. We'll see the setup available in our laboratory. We'll discuss the readings, how to have the readings and all that, and after that we'll make the calculations for the theoretical COP as well as actual COP. We'll compare both of them and we'll conclude the today's session. The conclusion part is very important part. You can continue till end. So if you see the prerequisites, we'll have to discuss the Clausius statement of second law of thermodynamics, which speaks about refrigerator and heat pump. Then we'll see concept of heat pump and simple vapor compression cycle. We'll see the TS and pH representation, analysis and its coefficient of performance. So let us start with the Clausius statement. What Clausius has said that if I want to transfer the heat from low temperature to high temperature with using a cyclic device, this is not possible. This is not possible spontaneously, right? Naturally this will not happen. Heat will not flow from low temperature to high temperature. Use any kind of device unless and until you don't supply the work. You will have to supply some work input, then this is possible. This is said by Clausius, right? This is the second law of thermodynamics based on which the refrigeration and heat pump concepts are originated. So basically here what is he saying that if I want to transfer the heat from the low temperature with the help of a device, it is lifting the heat from the low temperature and transferring it to the higher temperature, to the source. For that it needs compressor power, then only this is possible. If I do not supply anything else, external efforts are not there, this is not possible. Refrigerator and heat pump, how they are obtained? Like if I want to cool something, the same device will be called as refrigerator, and if I want to heat something, the same device will be called as heat pump. So the principally both devices are same. What is the difference then? When we want to cool something, we will be focusing on this QA. If I want to cool something, so I will be focusing on this heat addition to the substance, means extracting from the space. So the temperature of the sink will go down, and that is the cooling process. If I want to do that, the device will be called as refrigerator. But if I want to heat something, I will be focusing on QR, heat rejected by this device to the space, and because of that temperature of the space will increase, and since its temperature will increase, the device will be called as heat pump. I want to pump this. So whenever I will be using the same device as heat pump, I will be insulating this space. So you must be clear about what is meant by heat pump. Heat pump is a device used to heat something, some space or anything. I want to heat anything, I want to increase its temperature, I will use the heat pump to increase the temperature. How do I do that? I take the heat from the low temperature reservoir, use some compressor power and add the heat to the higher temperature reservoir so that its temperature increases. And since I want to maintain the high temperature of this space, I will insulate that space. So that kind of mechanism or method is called as heating the substance with the help of heat pump. So now we'll be discussing what is the block diagram for that. As I said that if you are clear with this diagram of second law of thermodynamics, you can easily construct the block diagram of vapor compression cycle indirectly for heat pump. So how it is? There is a sink. So from low temperature reservoir we want to pick up the heat. So what we'll do? We'll put a coil. This coil will have a substance called as refrigerant. That refrigerant will be at low temperature and low pressure at this point. This is at low temperature, low pressure refrigerant. The temperature of the refrigerant will be in minus. What will happen then? And this will be in liquid form. So this liquid refrigerant will enter into this coil, will absorb the heat from the the sink, and because of the heat is absorbed, the substance will boil and it will become vapor here. So once vapor is obtained, but still this vapor is low temperature and low pressure. right? I want to increase the temperature of the source. I will need high temperature, high pressure vapor. So for that what I'll do, I'll use compressor here. So after this, I'll use compressor. So you can observe that the diagram is getting prepared exactly in the same parallel format like this. So there is a compressor power. So after this thing, there is a compressor power. So I'll supply that high pressure, high temperature vapor, high pressure, high temperature vapor, because compressor will increase the temperature and pressure of that vapor. Now that vapor I'll supply it to the condenser coil. That is my objective now. Here the coil will reject the heat to the space I want to heat. So this heat is now rejected by the coil, and the liquid will convert, vapor will get converted into liquid. So once I get this liquid at the side, this liquid is still high pressure and temperature is also considerably high. So I got high pressure liquid, right? The objective is finalized now. I have got the heat, so I will trap that heat into a chamber or space which I want to heat, and thereby I can increase the temperature of that space. So that is how heat pump works. So we have trapped the heat rejected by the condenser into the space which I want to heat. Because of the heat is getting trapped here now, the temperature of the space will start increasing, and that is how we have achieved our purpose of heat pump, right? It is exactly same as the vapor compression cycle used for refrigerator. Only difference is that in that case we were focusing on the QA part. We were insulating this part of the evaporator. So this device is evaporator. Since why it is called as evaporator? Since the liquid gets vaporized, so this device is called as evaporator. Now we are not focusing on the evaporator. Evaporator is open, but condenser part of the device is now the space is getting insulated with the help of chamber, so that heat can be trapped. And now once the high temperature, high pressure liquid is obtained here, I want to reduce the pressure and temperature of the liquid. So I will use the expansion device, and thereby I can again achieve low pressure, low temperature liquid. I have discussed all the details of vapor compression cycle in the previous session. You can go to the playlist and you can learn from there. Now we'll learn how to represent this vapor compression cycle on TS diagram. You can see there will be two pressures. One is the evaporator pressure, that is Psat1. Low pressure side is a Psat1. Higher pressure side is a Psat2. So what I'll do first, I'll plot Psat1 and Psat2 on TS curve first. So let's say Psat1 and this one is Psat2. So these are the constant pressure lines. So at the end of evaporation, I have got saturated vapor that I will supply to the compressor. Compressor will increase its temperature and pressure isentropically. So the vertical line will show me the isentropic process. I will reach to point number 2 where the temperature pressure is high. So that is, let's say temperature T2 is superheated vapor. Now here I have got superheated vapor because the temperature is greater than its saturation temperature Tsat2. It is greater than Tsat2. So that is why it is superheated. So once I will get the superheated vapor, I will supply it to the condenser. In the condenser, first part of the condenser will desuperheat the vapor, that is degree of desuperheating. Then it will reject the heat to the space I want to heat, that will be latent heat part, and it will get condensed into liquid. Then liquid may reject the heat again and may get subcooled up to point number 3. So this entire process happens into a condenser coil where the superheated vapor gets desuperheated, gets condensed and gets subcooled, and I get a subcooled liquid at temperature T3, right? Now I will supply that liquid into the expansion device where the pressure will drop, enthalpy will remain constant. That is why this is called as isenthalpic process, and I will get point number 4 where temperature is 4. So here I have got liquid vapor mixture, small part of vapor and larger part of the liquid, that I will supply to the evaporator. Now the evaporator will evaporate this into vapor by absorbing the heat from the space lower temperature sink, thereby completing the cycle. So this is what the TS representation of the simple vapor compression cycle. So if I want to see the pH representation of the simple vapor compression cycle, this may go in the same fashion. So the starting point, let's say the saturated vapor at the inlet of compressor. Now isentropic line on the pH diagram looks like this. So it is isentropic compression. Then I'll get point number 2, which is a superheated vapor. Then I'll desuperheat it into the condenser. So the first part of the condenser is desuperheating, then there is a condensation, and then there is a subcooling. It will follow the constant pressure line. So thereby I get point number 3. From here there will be isenthalpic expansion, enthalpy will remain constant, and I'll reach up to point number 4. So here H3 is same as H4, and here S1 is equal to S2. Entropy remains constant, here enthalpy remains constant. The liquid will enter into the evaporator, will get evaporated, and it will absorb the heat from the low temperature reservoir. So that is QA. Similarly, the condenser has rejected the heat that we have trapped into a space, insulated space, and thereby we have achieved the heating effect. So that is how the vapor compression cycle looks on the pH representation. So if I want to analyze the vapor compression cycle, I must be able to find out the enthalpies at these different points. So if this simple vapor compression cycle is like this, how to find out H1, H2, H3 and H4. So to find out the value of H1 can be obtained with the refrigerant table of the given refrigerant. The H1 is on the saturated vapor line, so I can obtain the value of Hg. This value has to be seen in the table at Psat1 because it is at lower pressure line. So from the table at the Psat1 pressure, what is the value of Hg? That is nothing but H1 as per this diagram. Now second is H2. H2 is what? It is in superheated zone. Where is H2? It is in superheated zone. So it is above this superheated point. So this is Hg plus Cp delta T. I have explained this in previous session also in detail. Hg at Psat1, sorry Psat2, because point number 2 is on the higher pressure line. So Psat2, this Hg plus Cpg delta T. Delta T means what? Degree of superheat, T2 minus Psat2. So it is T2 minus Psat2. This is what this is from the part of thermodynamics, phase change phenomena of pure substance. If you have learned that, you can write down this. So if you want me to make the videos on thermodynamics as well, you can comment me. I'll be making on the complete playlist of thermodynamics as well to make these all concepts clear. So please comment if you want. Next is H3. H3 is where it is in subcooled zone. So where is how to find out H3? HF minus Cp delta T, because it is backside of the F. This is line of fusion. Yes. So previous to the F, that is why HF at the higher pressure line Psat2. From this HF we'll have to subtract Cp liquid, because this is liquid zone, this is gaseous zone. So Cp of liquid zone into delta T, degree of subcooling, Tsat2 minus T3, higher temperature minus lower temperature, Tsat2 minus T3, and this value is exactly same as H4 because the process 3 to 4 is isenthalpic process, enthalpy remains constant. That is why H3 is same as H4. So in this way we have obtained the 4 enthalpy values by having the refrigerant table. So next we will see what is meant by coefficient of performance for the heat pump. In the previous session we have seen what is meant by coefficient of performance for the refrigerator, because for refrigerator the objective is to cool something. So in that case objective is to cool something, this space I want to cool, so QA will be important. So output is my QA, input is work of compression. So QA upon work of compression, refrigerating effect upon work of compression is COP for refrigerator. You can remember, you can recall, COP for refrigerator is what? Output is QA, refrigerating effect, input is work of compression, work supplied, input. So that is what the coefficient of performance for refrigerator. But in this case we are discussing heat pump. So for heat pump the COP can be written as, again the basic formula is same, output upon input. So what is output? Output for heat pump and input for heat pump. Output for heat pump means what? objective of running the heat pump. What is the objective of running the heat pump? To heat something. If I want to heat something, QR is important. If higher the QR, better the heating will be. Higher the QR, better the heating is, right? So objective of running this heat pump is to heat something. If QR is higher, my performance will be better, temperature will be better. So that is why output of this device is QR. So QR is my output, and what I am supplying to do that? I am supplying compressor power in terms of work energy. So that is my input, right? So this is what the COP of heat pump. Now I want to write down that in terms of enthalpies. If I want to express that in terms of enthalpy, what is QR refrigerating effect is m dot into higher enthalpy divided by higher enthalpy minus lower enthalpy. What is QR? H2 minus H3. What is QR? H2 minus H3. So m dot into mass flow rate of the refrigerant H2 minus H3 divided by what is compressor power? Compressor power H2 minus H1. H2 minus higher enthalpy minus lower enthalpy. So m dot into H2 minus H1. So that is how we have got the coefficient of performance for heat pump. M dot can be cancelled and you can find out this ratio. If I know the values of in these enthalpies, I can find out the COP of heat pump. So m dot can be cancelled. So finally I get H2 minus H3 upon H2 minus H1. So if I know the values of enthalpies at different points, I can find out the coefficient of performance theoretically. Now we'll go for the heat pump test rig. I know the basic cycle. I have the 4 basic components of the vapor compression cycle arranged. Now my focus is to heat something, so QR is important. And now I want to construct the heat pump test rig. Test rig is something which allows you to measure the performance of this system. That is nothing but the test rig. So to measure the performance of the system means what? We want to find out the coefficient of performance. So finding out the coefficient of performance means what? Finding out H1, H2, H3 means enthalpies at different points. If I want to find out the enthalpies at different points, what is the formulation I have? I have the formation like this, right? What is this? I can obtain the enthalpies of the gaseous phase at the different pressures. So I must know the pressures, right? Psat1, Psat2. Similarly, I want these temperatures at different points. Means if I want to construct the test rig to measure the theoretical COP of the refrigerant, theoretical COP of the heat pump, I must be able to measure 4 temperatures at 4 different locations. I must be able to find out the pressure in the evaporator, find out the pressure in the condenser, that is before compressor and after compressor. So that is how I can modify these 4 components by putting the 4 thermocouples at 4 locations. So you can observe I have written point number 1. So indirectly this is a thermocouple. Point number 2, this is second thermocouple. Point number 3, this is third thermocouple, and fourth thermocouple. So these 4 thermocouples will record the temperatures of the refrigerant at that particular location. Then we'll have to mount the pressure gauges. So I'll mount suction pressure gauge at the inlet of the compressor. So let's say this is the pressure gauge at the inlet of the compressor. Psat1 will measure the pressure at the inlet of compressor. Similarly, I'll mount the discharge pressure gauge after the compressor, that is condenser pressure. Pressure gauge mounted at the condenser inlet, that is compressor exit, Psat2. So Psat1 and Psat2 will give me the values of pressure. 4 thermocouples will give me the values of temperature. From this I can plot the theoretical, I can plot the TS representation. From that I can find out the 4 enthalpy values, and from that I can find out the theoretical COP of the cycle, right? Now I want to find out the actual COP of the cycle. To find out the actual COP of the cycle, I must be able to find out this refrigerating effect, compressor power, or heat rejected in actual form. So how to do that? In the particular setup which I have in my laboratory, whatever the arrangements they have done, I'll describe here. This is not necessary that this arrangement should be like this only. You can make the alternative options also. So what they have done, they have modified this condenser and evaporator in a coil tail and coil heat exchanger form. So what they did, so they have put a coil here. The coil is inserted into a chamber, right? So point number 2, I'll connect it here. Here is the second thermocouple. Pressure gauge, I'll put this pressure gauge here. so that I can measure the compressor pressure. Now this coil will be placed in a chamber because we want to construct the heat pump. I will place this coil in a chamber and will insulate this chamber to avoid the heat loss to the atmosphere. And in this chamber we'll use a secondary medium like water. We'll put water into this. Known mass of water is, and we'll put a thermometer here in the coil to measure the temperature of this water. To monitor the temperature of this water, symbolically I am showing the thermometer like this, but of course that will not be a mercury type of thermometer, but symbolically I am showing it like this, right? So there is a thermometer which will monitor the temperature of the water. There is a coil which will transfer the heat to the water. So now by some means, if I am able to find out how much heat is rejected by this coil to this water, that is my heating effect. By some means, if I am able to find out how much heat is rejected by this coil to this water, if I by some method I can find out this, then I can find out the heating effect. Fan here, turbulator or stirrer we can say, that will stir this water so that the boundary layer will not set up and the proper uniform temperature of the water can be obtained. So known mass of water, let's say this mass of water is mass of hot water, which is known to us. The volume of this shell is known, density of the water is known. You can find out the mass of the water, right? The temperature, initial temperature, final temperature will record. I'll discuss the methodology how to find out that heat transfer rate, but the primary mechanism is that we are going to reject the heat from the condenser coil to this water, and we'll record that to find out the actual heating effect, right? Similarly, what we'll do now, we'll modify this evaporator as well in the similar function, similar format. We'll modify this evaporator. This is evaporator coil. We'll keep the same in the same format. We'll keep it in a chamber filled with water. So the refrigerant inside this chamber will absorb the heat from this water, and that is nothing but the heat added to the refrigerant QA, right? And the water will get cooled. So again, the known mass of water is kept in this chamber. We can monitor the temperature of this water as well. Mass of cold water, right? I will monitor the temperature using a thermometer. Okay, so this is what the arrangements I have done to find out what is how much heat is absorbed. So if I by some means, if I am able to find out how much heat is absorbed by the refrigerant from the water, I can find out the QA. Yes, you can measure the actual compressor work also, but in this method what they have done, by first law of thermodynamics, we know that the summation of Q equal to summation of W. So if I am applying summation of Q equal to summation of W, what will happen? Q added is the positive, heat added to the system is positive, heat rejected by the system is negative, equal to work of compression is supplied, so it is negative. There is no any other work. So from here we can obtain that work of compression as QR minus QA, right? This minus will go to this side, so it will become QR minus QA. So this QR minus QA formula can give me the work, compressor work, actual compressor work, right? Heating effect is my objective, so QR upon this WC is my actual COP, right? Here now I want to measure the mass flow rate of the refrigerant. For that purpose I can use the rotameter, and dryer can be installed here. Dryer is to filter the refrigerant from any wetness, right? And as well as the filter from the impurities. That is, dryer is used, and then we can use rotameter to measure the mass flow rate of the refrigerant, so that I can use it in calculations if needed. That is how the rotameter is installed inside this circuit. Then there will be expansion device. Expansion device we are going to use, that is nothing but capillary tube. So that is how we are modifying the setup. Whatever setup we have in our laboratory, I am constructing that, right? So this is how the capillary tube is installed. Okay, then the refrigerant here, HPLP cutout is used to protect the compressor from any damage, sudden pressure rise or sudden pressure drop. So HPLP cutout is used. We can install a compressor energy meter to record how much compressor power, or otherwise we can use this formula to find out the compressor power, actual compressor power. So this is what the heat pump setup is. where we have two shell and coil type of heat exchangers. One is for evaporator, other is for condenser, right? The water is used as a secondary medium between the heat exchanging medium. Now we'll monitor the temperature of this water, hot water and cold water, and we'll record them and we'll find out how much heat is added or rejected, right? So this is what the experimental setup is. Now I'll show you the actual photograph. You can see this actual photograph that is available in our lab. There is a evaporator shell, as I said. This is a shell and coil heat exchanger. I'll show it that in video also. Then there is a compressor in between them. So refrigerant after evaporator will go to the compressor. Then it will go to the condenser. Condenser is a red tank shown. That is again a shell and coil kind of heat exchanger. And from there it will go to the capillary tube. In the circuit there is a pressure gauge, HPLP cutout, dryer. There is energy meter for the compressor. Then there is a temperature indicator which will record, which will show us the temperatures at different locations. The compressor switch is there and main switch is there. This is what the heat pump setup is. Now these are the specifications. So you can read the evaporator and condenser tank size. Whatever the tank size we have selected for the evaporator and condenser shell, that is nothing but 280 mm of diameter and 230 mm of height, right? Then there is a refrigerant used is R134A. Energy meter constant is 3200 impulses per kilowatt hour. Then assumptions we are making that atmospheric pressure is something 1.01 bar, water density is assumed to be 1000, water Cp is assumed to be 4.187 kilojoules per kg Kelvin. Now record to record the readings we need observation table. So the observation table to find out the actual COP, theoretical COP of heat pump is like, we'll measure the suction pressure gauge and discharge pressure gauge. We'll find out the temperatures at different locations: compressor inlet, compressor exit, condenser exit, and expansion device exit, right? So these are the 4 locations. Temperatures will record. I suggest you to note down this observation table in your notebook before going for the trial. This observation table is for actual COP. As I said that what we'll do, evaporator shell we have put water, that will give us the QA. To find out that, what we'll record first, before starting the setup, what is the water temperature, that is cold water inlet initial temperature, and after some time of 1 or 2 hours, what is the final temperature of that water, right? Similarly, what is the initial temperature of the water available in the shell of the condenser, hot water initial temperature. Obviously these both temperatures will be same initially. The evaporator water temperature will start decreasing and the condenser water temperature will start increasing. So we'll record that both readings after equal time. We'll keep the time same for both so that time can be cancelled, right? We'll keep the mass of the water in the both tanks to be same, so that when I will find out the heat transfer, that is m Cp delta T divided by time. So if I want to find out this for condenser shell, I'll take Cp delta T of the condenser. Mass and time is same for both. If I want to find out for evaporator, I'll take Cp delta T of the evaporator. Delta T is what? Final temperature minus initial higher temperature minus lower temperature, right? By this way we can find out the actual heat exchanges, and we know that COP, what is COP of heat pump? It is QR upon QR minus QA, because compressor power is QR minus QA. So by this way we can find out the actual COP of the heat pump. So note down this table in your notebook, and now we'll go to the setup. We'll allow the setup for steady state and then we'll take the readings, then we'll come back for the calculations. So this is our heat pump test rig, where you can observe that the evaporator and condenser both are shell and coil type of heat exchangers, where this is a cylindrical shell in which there is a evaporator coil, copper evaporator coil, and again this condenser is also same. This is a cylindrical shell in which there is a copper condenser coil, and filled with the water with the stirrer to maintain the constant temperature of the water. So the cycle is like, first evaporator, after the evaporator there is a compressor, after compressor there will be a condenser, and the exit of the condenser is connected to the capillary tube, and in the exit of the capillary is connected again to the
evaporator. So in this way vapor compression cycle completes. In the cycle, suction pressure gauge and delivery pressure gauges are mounted before compressor and after compressor to get the pressures. This is the HPLP cutout for the electrical safety. Then this is a dryer to absorb the moisture from the refrigerant liquid, and this is energy meter connected to the compressor. This is temperature indicator, and this is switch for the compressor. So to start this, we have to set this for steady state at least for 2 hours. So let us begin the trial. I will switch on the main switch. So here you can see that the stir action is there. It is continuously stirring the water to keep its temperature constant. Then there is a stirrer to this side also. Now let us switch on the compressor. So with this switch I will switch on the compressor. So now the compressor is on. Now we can observe that delivery side pressure is getting increased and suction side pressure will drop. And initial temperature of the water is 21.4 degrees Celsius. So this is the initial temperature of the water. So after at least 2 hours we are going to get the reading. Now it is almost 2 hours, so that we can take the readings. So record the suction pressure of the compressor as 0.5 kg per centimeter square. This is the gauge pressure, and the condenser pressure or the delivery side of the compressor is at 8.5 kg per centimeter square. Now the temperatures. So inlet of the compressor is at 21.4. Exit of the compressor is at 64.9. Then after condenser it is 23.5, and after expansion device inlet of evaporator is at 8.3. Then evaporator water, whatever the water we have kept in the evaporator chamber, that is getting cooled, so its temperature is 19.8, and the water we have kept in the condenser shell which is getting heated, so its temperature is 24.3.
So these are the readings that we have taken from the setup, right? We have found that Psat1 is 0.5 and Psat2 is 8.5. Note that these are the gauge pressures and the temperatures at the different locations. Then we found that what are the temperature changes in the evaporator shell. The temperature dropped from 21 to 19, and in the condenser shell temperature increased from 21 to 24. Okay, I will explain them one by one. So step number 1 will go for the converting the gauge pressure into absolute pressure. Now to convert this gauge pressure into absolute pressure, firstly what we'll do, we will convert this kg per centimeter square into bar. So to do that, I will convert that 0.5 kg into Newton by multiplying it with 9.81. This is Newton. Now I want to convert this centimeter square into meter square. For that I will multiply it with 10 to the minus 4, and this will become now Newton per meter square. So this becomes Pascal, right? I want to convert this Pascal into bar. So for that I will multiply it with 10 to the 5. So now it has become bar, right? So if I calculate this, so it comes to be 0.49 bar. But now this is a gauge pressure. I want to find out the absolute pressure, absolute suction pressure, gauge pressure plus atmospheric pressure. If I want to add here, atmospheric pressure is 1 plus 1.01325 bar. So it becomes 1.5 is approximately equal to 1.5 bar. We have got the absolute pressure at the suction of the compressor is 1.5 bar. In the similar process, I will make it for Psat2 9.4 bar. We have got these values of pressures at inlet and exit of the compressor. Now we will find out the different enthalpies at different locations. So that can be obtained from the refrigerant table of R134A. We'll find out the refrigerant table of R134a at 9.4 bar, that is condenser pressure. How much is the boiling point that will obtain? That is 38 degrees Celsius is the boiling point. We have got at this pressure. How much is the pressure? 9.4 bar. So at 9.4 bar, 38 degrees is the boiling point, right? Similarly, we have got that at 1.4 bar, 1.5 bar, boiling point is minus 16 degrees Celsius for R134a, right? Then we found out Hg. For PSAT 2, how much is the Hg? Hg value that comes to be 418. What is CPG at this point? CPG, then HF 253. Similarly, we find out Hg at lower pressure, that comes to be 389, and CPG at that point is 0.831. So this data we have obtained from refrigerant table, because these 3 points are important, 1, 2 and 3. So we have obtained all the data from the refrigerant table for that particular pressures. Now we'll plot the actual TS diagram for the given readings. So we have obtained that the PSAT 2 is 9.4 bar and PSAT 1 is 1.5 bar. Boiling points, corresponding boiling points, I'll plot on the diagram, that they are the boiling point of the condenser is how much? 38 degrees Celsius, and the boiling point of the evaporator is how much? Is minus 16 degrees Celsius, right? Then now we'll start with point number 1. So point number 1, let us observe the readings. T1 is how much? 21.4. So it is minus 16. 21 must be in superheated zone. So 21 is somewhere here, let's say. So this is point number 1 of the compressor. Temperature T1 is something 21.4. Right? So from here compressor will start. At what point compressor will end? Temperature at the exit of the compressor is 64.9. So it is again greater than 38. So it is greater than 38. So it is superheated. So it is how much? 64.9. This is what point number 2. Temperature is 64.9. Then if I go to T3, it is 23.5. 23.5 is less than 38. 23.5 is less than 38. So point number 3 will be in the subcooled zone. Point number 3 is less than 38. How much it is? 23.5. There is a subcooling as well. So now this becomes condensation. There is first desuperating, then there is a phase change, there is a subcooling. So this total becomes QR, heating effect. This 1 to 2 will not be polytropic. This is practical process. So this we don't know the path. So I am showing it random path, polytropic path of the compression process, right? Then there is a expansion. Now at what temperature? Expansion ends 8.3, much above minus 16. It is above minus 16. So expansion ends at 8.3 degree. Expansion ends at 8.3 degree, like this. This temperature is what? 8.3 degree. Here, and from there now evaporation will start. So there is a pressure drop in the evaporator, we can observe. There is a pressure drop in the evaporator. There is a superheating. So by this way the process 4 to 1 completes. So this is point number 4. So 4 to 1 is the heat addition process. This is heat pump, so we will not call this as refrigerating effect because we are not focusing on that. Our objective is to heat, so QR is important. Input is compressor power. So this is what the actual TS diagram of the given readings. From here now we will find out H1, H2, H3 and H4. So what is the formulation required for H1? What is H1? It is in superheated zone. Where is H1? H1 is in superheated zone. So it is Hg plus Cp delta T. What is Hg? Which Hg we will have to take? We will have to take it at lower pressure, PSAT 1 from the refrigerant table, plus Cp in the gaseous phase, because it is in gaseous phase. This is gaseous phase, this is liquid phase. So we are in gaseous phase. So Cp gaseous at that pressure, we will take this from the refrigerant table into delta T, degree of superheat, T1 minus Tsat1, T1 minus Tsat1. So if you put all these values, I have given already T1 minus Tsat1, you will get the value of H1, right? So put the value of all values, find out this H1, answer will be in kilojoules per specific enthalpy we are getting in kg. Similarly, we can find out H2. H2 is again in superheated zone. If you observe, H2 is in superheated zone, but it is now compared with the Hg of gas, the Psat2 9.4 bar. So it is Hg at Psat2 again plus Cp delta T. Cp gaseous phase at 9.4 bar. Delta T is how much? Degree of superheat here is the T2 minus Tsat2. Degree of superheat T2 minus Tsat2. So from here I will get H2 as kilojoule per kg. Now we'll go for H3. H3 is equal to, where is H3? Here. So it is before HF. So HF minus Cp delta T. So I'll find out HF of what? At higher pressure line, that is Psat2. It is on higher pressure line, 9.4 bar HF value, 9.4 bar HF value minus Cp delta T minus Cp of liquid. I'll have to take liquid because it is in point number 3 is in liquid zone. So Cp of liquid delta T will be degree of subcooling. How much? Tsat2 minus T3. Tsat2 minus T3. This is the part of thermodynamics from phase change phenomena of pure substance. So H3 is same as, now we know that H3 is same as H4. So once we get H3, you will get H4 as well, which is same as H3 and H4 both are same. So once we do these calculations, do it now with your own calci and find out the answers. You will get the answers like this. So we'll get H1, H2, H3 and H4, which I have already found, and these values are like this. Now we'll go for the calculation of theoretical COP. As I said that theoretical COP for heat pump is what? The objective of heat pump is what? To heat something. So heating effect upon input power. So it is what? QR upon compressor power. So what is that? QR is what? H2 minus H3 m dot into m into, if I take the rates of the transfer or work transfer, then Q dot will be there, then m dot into H2 minus H3 divided by m dot into compressor power H2 minus H1. So from here the same mass flow rate of the refrigerant is passing through compressor and condenser. With whatever mass flow rate the refrigerant is passing from the compressor, the same mass flow rate is maintained in the condenser as well. So the mass flow rate gets cancelled. Yeah, we know we have these all values. If you put all these values, you will get the answer as 7.54. COP theoretical. Now these are the arrangements we have already discussed. For the actual COP, we have used the evaporator, shell and coil type of evaporator, shell and coil type of condenser. So how to find out the condenser heat? QR can be obtained as mass of the known mass of the water we have placed, the Cp of the water, right? Then what is the temperature rise in the water? So final temperature of hot water minus initial temperature of the hot water. This is the heat gained by the water in the condenser shell, right? This is the amount of heat absorbed by the water in the given time. So this is the rate of the water, the rate of the heat by which water is getting heated. Similarly, we can obtain QA in the evaporator. So mass of the known water, we have mass of the water known here, Cp of the water, then the temperature of the water in the evaporator has reduced because heat is absorbed from the water. So that is why the initial temperature will be higher. So TCI, cold water initial temperature minus cold water final temperature. Final temperature will be lower, initial temperature will be higher. So higher temperature minus lower temperature delta T divided by time required for this this process. Now the time required for the both processes is same. We have taken the known mass of the water and we have made it identical. Whatever the mass of the water kept in the condenser was same as the mass of water kept in the evaporator. So this MCP gets cancelled, time gets cancelled. So now to find out the COP of the actual COP of the heat pump, what is the actual COP of heat pump? We have already described that it is cooling heating effect upon compressor power. And first law of thermodynamics says that compressor power is nothing but QR minus QA. That I have explained already. Compressor power क्या आएगा? QR minus QA. So if I put all these here, MCP will be common, time will be common, that will get cancelled, and you will have the values of these four temperatures. Put them, you can find out the actual COP. Do it now. You will find that actual COP is 2.23. Now we'll go for the conclusion. So if I want to discuss the conclusion of the today's session, if I summarize the today's session, we have seen how to construct the setup, how to set it for the theoretical COP as well as actual COP. We have used the shell and coil type of evaporator and condenser, right? We have used thermocouples to measure the temperature, pressure gauges to measure the pressures at the two locations. So now we have got the COP of the theoretical COP as 7.54 and actual COP to be 2.23, right? Now we'll discuss why these values are differing with each other. There are certain reasons, like first one is we have mounted thermocouples at different locations that are insufficient number of thermocouples. Like if I mount one thermocouple between evaporator and compressor, that is not sufficient, because once the vapors comes out of this evaporator coil, it absorbs the heat from the atmosphere as well, right? And if I mount thermocouple here, the heat absorbed from here to here, it is absorbed outside the evaporator, which we are counting as a cooling effect. In the similar way, we have mounted compressor at this point. Now we are considering that the heat in this region, rejected heat is in the condenser heat, that is not actually. So that is why the one thermocouple is not sufficient at in between the two devices. The number of thermocouples are insufficient. Second is like error in temperature measurement. So whatever thermocouples we have used, they are not calibrated and they are mounted on the outside surface of the tube. They cannot record the exact temperature of the refrigerant which is inside. There may be error in the temperature measurement. There may be error in the pressure measurement, because we are assuming that whatever pressure gauges we are using, the readings are taken at particular location. Let's say Psat1 is taken here, but this may not be pressure exactly here because of the actual pressure drops, like momentum and friction pressure drops are there. So that is why the pressure may be different during this tube. We are assuming that the heat addition and rejection are at constant pressure, but in actual they may not be, and that is why the variation is there, right? So these are the different reasons because of which the experimental value, the theoretical value varies with the actual value of coefficient of performance. I hope you enjoyed this today's session. If you have any kind of suggestions, you can comment me in the comment box. If you like the video, please hit the like button, share with your friends. Thank you very much.